Okay, hello everyone. In our previous discussion where we implemented the linear regression model from scratch to a machine learning model and we made the predictions. So we optimized the use of the cost function a lot and it helped our model perform better. But someone asked a question which I think I should talk about it or address it. Remember, in obtaining the error, we said we get the predicted value, which is y hat for this case minus the true value, and we said that this value, this difference can actually give us a negative value which we do not want. So we have two options, or we add the two options by either taking the square by either squaring this value or taking the absolute of that difference, right? Or taking the absolute value of that difference. And we said that it is more better we take the one with the square, as you saw in our cost function that it was dealing with the square up here, not the absolute value. So someone asked, why are we taking this option where the cost function is dealing with the square and not the absolute value? Remember, we saw the cost function and how it looks like. I'm not going to dive into that now, but I'm addressing why we take the one with this. We take the square. Why is it uses the square, not the absolute value? So this will give us the error, right? So the mean squared error, we discussed this and how we came up with it. We realized it had some square here somewhere. So someone asked that, and in order for us to address that, then we need to look at the probability interpretation of the linear regression. So it will help us understand why the square and not the absolute value, right? So if I can drop you back to our model, y is equal to the transpose of theta xi plus the error term, which is a hat. So this was our linear regression model, the one we implemented earlier. So whereby this error term was representing the non-parametric factors which affects the model. For instance, we looked at the prices, the factors which, we use the example of predicting the rent prices of buildings in Kampala. So, and we said some of the factors which would affect the price, actually we saw that some of the factors which was affecting the price value, the rent value, was the street on which the building is and the size of the building or the room you are trying to rent. So, but remember, there are some other factors which we may not directly model into and can be represented by the error term. For instance, assuming you use the broker, and this broker in one way or another hypes the rent value, maybe because his children is being chased by, for school fees, or is sick and they need to get something, so you land on him and he hypes the prices of the rent so that he can meet his responsibility. So there are those kind of factors and they are all captured here, which we would call the noise. So, and why am I explaining that? Because in order for us to answer the other question, it's all about the error, where our cost function was capturing the error made. So that's why I had to emphasize that. And looking at the assumptions of linear regression, which we discussed in details and proved in our model. There's one which says that the error term is normally distributed, the normality of error. So that means that the error term follows a normal distribution given by mean 0 and the covariance given by sigma squared. So literally meaning our error term follows a normal distribution. This is the mean, which is 0. The mean is 0 and the covariance is given by sigma squared. So having said that, since the error term follows a normal distribution, that means that its probability density function is given by is given by 1 over 2 pi sigma exponent of negative error term squared over 2 sigma squared. So that is the probability density function of the error, because it follows a normal distribution. Now, taking the assumption that the error term is independent, I think we saw that among the assumptions of regression that the error term are independent of one another. Literally, if this what I can, okay, let me illustrate that here. We discussed this in details, but maybe to remind you that if in our first prediction we get error 1, and in the second prediction or during the training phase we get another error 2, and so on and so on, this assumption says that they are actually independent of one another, and we saw that in details. So since they are independent of one another, this implies that the density of probability y, the probability density of y, which is yi, right? That is subscript I to imply iteration. The probability density of y given xi parameterized by theta to be equal to, allow me put it here, to be equal to 1 over square root of 2 pi sigma exponent of minus, literally what we are going to do, we are going to put the value of the error term, and the value of the error term from our equation here, from that equation, the error term, which is yi, will be equal to y minus transpose of theta xi. That is the error term. So this is what we are going to substitute in the other equation. So it will be into yi minus the transpose of theta, or the model parameter xi squared over 2 sigma squared. 2 sigma squared. So that is the probability density function of y given x I parameterized by theta. So literally that means it follows a normal distribution as well. So the probability density function of yi given xi parameterized by, I'm using a semicolon to imply parameterized by theta, follows a normal distribution. Follows a normal distribution. Though for this case, the mean will be given by the transpose of theta. The mean will be given by the transpose of theta, xi, and the covariance will be given by sigma squared. So that's what it means. Right? Now we are going to look at the likelihood. We're going to look at the likelihood of parameter theta. And the likelihood, allow me use L, small l, to imply the likelihood of parameter theta. The likelihood of parameter theta will be equal to the probability of the data. And we see probability of the data, that is the probability of y, all values of y. The probability of all values of y given all values of x parameterized by theta. So the likelihood of parameter theta will be given by the probability of y, right? Now, since we are still looking at the independence of the error, therefore the probability of all the observation is equal to probability. The probability of all observation, the probability of all observation, which is this, the probability of all observation, the probability of all observation, the probability of all observation will be equal to the product of the probability, to be equal to the product of all the probability, where I is equal to 1 up to m, to be equal to the product of the probability, where I is equal to m, equal to I, the product of the probability yi given xi parameterized by theta. So we said the likelihood of parameter theta, the likelihood of parameter theta is equal to the probability of all the observation. And the probability of all the observation, which is this, the probability of all observation is given by the product of all the probabilities. So, but we know the value of this, right? We know the value of this from here, right? From there. So we substitute that value. Therefore, the probability of all observation will be to the product of all the probabilities. Product of all probabilities, where y is equal to 1 up to m, y is equal to 1 up to m into 1 over the square root of 2 pi sigma, 2 pi sigma exponent of 2 pi sigma exponent of negative yi minus the transpose of the parameter, which is sigma xi, this is squared over 2 sigma squared. So now the probability of all the observation is given by this, which is the product of all the probabilities, right? Therefore, Now, if we look at the log likelihood of the parameter, if you look at the log likelihood, this is the likelihood of parameter. If you look at its log likelihood, it will be log of the likelihood theta, parameter theta, to be equal to log of the likelihood parameter theta. Now, taking this log likelihood to substituting this, remember we are looking at the likelihood of theta, which is here, and now we are going to substitute it here, right? So it will be log of the product, log of the product of the probabilities, which is I is equal to 1 to m, I is equal to 1 to m into 1 over the square root of 2 pi sigma exponent of negative y minus the transpose of the parameter x squared over, over 2 sigma squared. So that is the log likelihood. And remember, in logarithm, the product of log is equal to the sum of the log. For instance, if you have log A, log B is the same as log A plus log B. So we are going to take that log in play. So that will give us the summation of I is equal to 1 up to m into log, because why are we saying that? Because this equation has two parts, has this one, has this, and has this, the exponent. So meaning there is a product, it is a product of these two parts. So, and remember, it's all under the logarithm. It's all under the logarithm. Therefore, that's why we said that we take the root of having log A, log B. Log B is the same as having log A plus log B. So that's what we are going to do here. That's what we are doing here. So it will be having log 1 out of square root of 2 pi, square root of 2 pi sigma plus log of exponent, negative 1 minus transpose of the parameter x squared over 2 sigma squared. So that is the rule. That's what the rule dictates. And once we look at this here, this is a constant, so it has nothing to do with the theta. It is a constant and it has nothing to do with the theta. So this is the same as having, and it goes up to m, so it will be m log 1 over square root of 2 pi sigma plus this is going to give us the summation of I is equal to 1 up to m into negative yi minus the transpose of the parameter, which is theta xi squared over this over 2 sigma squared, 2 sigma squared, 2 sigma squared. So that's what we will be having. And you see, the best, or we well know that the best method for testing parameters, I mean the method in estimating parameter, is the maximum likelihood estimate. So the well-tested method in estimating the parameter, for this case which is theta, the best method in estimating the parameter is the maximum likelihood estimate. Is the maximum likelihood estimate, which means that we choose theta that maximizes the likelihood, right? In order for you to understand this statement, you need to have looked at the locally weighted regression. Locally weighted regression, just maybe to illustrate it here quickly, if we have a data which is like this, if we have a data which is like that, for linear regression we would fit a model here on this data, but for locally weighted regression it says that no, let us concentrate where we want to predict. For instance, if you want to predict a value here, let me say x, and this is the value we want to predict. For locally weighted regression, it says now let us, instead of putting into consideration of this whole data, let us only concentrate here by looking at the likelihood, the local likelihood, the data which is close to the value we want to predict, and then we draw the regression or the linear regression from there. So why is it that? Because we assume that this data, the weights or the parameter around this data carries more weight, so they maximizes the likelihood, right? For instance, we could concentrate on the data here, this data which is close to AX, and then because the parameters here, the thetas, carries more weight. The thetas for the parameter around these values carries more weight compared to the parameters which are here on these values, this side, they carries weight. Here we illustrate it by maybe drawing a shape, a bent shape, like that of a normal distribution, and you realize that for this, the one which is far from the value, like here, the one which is far from the value, it has actually 0, and the one close to the value, they carry a weight of 1. They carry a weight of 1. The one which is far carry a weight of 0. That's why this one may not that be important in order for us to predict this value. That's what the locally weighted regression dictates. So, meaning the weight or the parameter here close to these values carries more weight. In other words, they maximizes the likelihood compared to the weights of the parameter which are this side or very far from the value we want to predict, which carries less weight, otherwise indicated by 0. So that's what we are talking about. That's what that statement means, that we choose theta which maximizes the likelihood. We choose the theta which is too close to these values. So, and that's what we are going to focus, that knowledge, that's the concept we are going to look at here. So given our model here, given this model, which is if I can write it here, m log 1 out of square root of 2 pi theta plus summation of 1 is equal to I is equal to 1 up to m minus y minus the transpose of the parameter x squared over 2 sigma squared. So that one. So we choose theta, we choose the value of theta, which is this, that maximizes the likelihood. Now the value of theta which maximizes the likelihood literally minimizes the error, right? Because if we can go back here, you see that the values here, the theta around here, they carry more weight, so they maximizes the likelihood, and in other words, they reduce the error. So meaning this part, if you look at this part, this is Banang, this is sigma, okay? This is sigma. So this part actually has nothing to do with the parameter. So we consider that to be a constant, and we focus on this part which has theta. Therefore, we choose this part which maximizes the likelihood. Therefore, we are going to focus on that, which is a summation of I equal to 1 up to m into negative yi minus the transpose of the parameter theta, xi squared over 2 sigma squared. So this is the part where the parameter maximizes the likelihood. Now we said that the parameter which maximizes the likelihood, in other words, it minimizes the error. So, and remember here it is a positive, so it maximizes it is a negative, it's a negative here, so it maximizes the likelihood. In order for it to minimize the error, it has to change the direction. So it will be a positive value for that case. And if you look at these values, if you look at here, they have nothing to do with the theta. So they are constant, and they can be pulled out of that part. And therefore, we end up getting 1 out of 2 summation of I is equal to 1 up to m into this, change the sign from the negative to positive in order to minimize the error. So we get yi, transpose of theta, xi, transpose of theta xi squared over 2 sigma squared. Oh, no, we pulled that out, they are constant. So remain with that. And if you look at this, it actually brings out the cost function. It brings out the cost function, and this explains the 2 here. All of that been trying to prove where this 2 comes from, so that explains the 2. Therefore, we have our cost function like that, right? So I think I've explained everything, and thank you. And maybe I'll discuss the local weighted regression as well. Thank you.